Good afternoon, this is Enrico Vaccariello, and in this presentation I'm going to briefly illustrate the latest progresses of my PhD research that is about graph-based tools for the synthetic generation of energy network models with a focus on distribution gas networks. The reason behind my research work is the need for an urgent reduction in the emissions of greenhouse gases, not only for the power sector, but also for the gas industry and all the end-use sectors depending on it. In this regard, there is an increasing scientific and industrial interest in the direct deployment of hydrogen and other fuels, like biomethane, in the existing gas grids. But what can be the impact of these non-conventional fuels on the operation of the existing infrastructures and their end users? Further research is required to answer this question. However, there is a bottleneck represented by a general lack of available information about real-world gas networks, mainly due to industrial secrecy and privacy issues. In this framework, the aim of my research is developing synthetic models of gas distribution networks with correct topologies and realistic technical properties. Previous achievements toward this goal led to the creation of a model capable of mimicking real-world gas distribution grids. The model adopts a probabilistic approach, ensuring different results at each execution, and, as visible from the charts on the left, provides the synthetic networks with realistic spatial and topological characteristics. However, a technical design is still required in order to use these network models for simulation purposes. For this reason, the latest activities focus the assignment of these networks with technical properties, ensuring that the grids comply with target technical specifications. The tool developed for this purpose receives in input a network topology, the design parameters, and the nodal consumption at design conditions. After that, it proceeds with the sizing of spanning tree extracted from the network structure. As visible from the animated figure, the algorithm iteratively identifies the critical nodes featuring unadmitted pressure values and enlarges the pipelines serving them. The procedure goes on until all the critical pressures have been addressed. After that, the remaining loops in the network are sized as well. The step following the development of these tools has regarded the sequential generation of a large number, namely 10,000 synthetic network topologies, starting from a reference gas grid. This is shown in the animation on the top. These synthetic grids are therefore technically sized accordingly to the procedure illustrated in the previous slide. This process led to the creation of 10,000 ready-made case studies of medium pressure networks operated at 5 bar. In the process, some constraints have been applied to better control the properties of the output networks. These constraints regard the location of the gas supply node, the number of loops, and the spatial distribution of the gas consumption. Some structural and fluid dynamic characteristics are now derived for the synthetic networks obtained. It can be seen that, despite a significant variability, the values of the diameters and volumes of the synthetic networks are within sensible and realistic ranges. From an operational point of view, the velocities and pressures are always compressed within the required values. It can be seen that, despite the constraints applied, the distributions of the pressures are significantly variable. This result shows that even small changes in the network structures can lead to very different fluid dynamic behaviors. In a second stage, a further 10,000 networks have been generated, this time without applying any of the constraints of before. The pressure distribution of the networks obtained in this way are depicted in the right-hand side of the slide. As expected, the pressure distributions are even more variable than in the previous case. Summing up, the tool is capable of generating networks with diverse fluid dynamic responses. However, if some specific behaviors were desired, only those grids with properties sufficiently close to a specific target can be possibly kept. For instance, in the same chart, the pressure distributions are classified and colored according to their closeness to a target pressure profile, indicated by the Kolmogorov-Smirnov statistic. This information can be used to possibly exclude all those networks whose pressure profiles is too far away from the target. We have used, by means of example, the pressure profiles, but it is important to mention that any other target property could be used instead. As a conclusion, it has been shown that the presented tool produces distribution gas grid models with consistent topological properties, and that it is able to ensure that these networks always satisfy target technical requirements. It has been shown that the fluid dynamic response of these synthetic networks is significantly variable, even when constraints are applied. This result suggests that it may be extremely important to carry out studies on gas networks adopting a statistical approach, thus guaranteeing a broader validity for the results. Finally, it has been pointed out that, if needed, the different networks generated by the model could be possibly filtered based on the similarity to a given target property. The very next steps will be applications involving the distributed injection of alternative fuels like hydrogen, also in scenarios of coupled electricity and gas networks. And it is worth mentioning that this future works will take advantage of the tool's capability to adopt a statistical approach. Thank you very much for your kind attention.